Hi, here we are with lesson 2.8, solving exponential equations with non-like bases. So this first slide just reviews the like bases strategy that we learned a while ago. So 4 to the x equals 64. When you have a feeling about 64 that it can be written as a base of 4, you want to try that first. This is a simpler way of solving. So since they can both be written as bases of 4, 64 is 4 cubed, we write 4 to the x equals 4 cubed. Then you see that you have the same base. They're both bases of 4. You can get rid of the bases and simply write the exponents. X equals 3, and there you have your solution. We did more complex examples where we had to do algebra after this step, but this is a simple example of what we're talking about. Now, if you look at one like this, 3 to the x equals 5, there's no way of writing 3 and 5 with the same base. This is what we're doing today. We've looked at simple ones like this where we use the 7 rule to write this, since it's in exponential form originally, as a logarithm. So starting at the base of 3, we will write this as a log base 3 of 5 equals x, applying our 7 rule. Now in the notes it says that log base 3 of 5 is an exact value. That could be your final answer if we ask for it that way. Or you could put this into your calculator and round to the nearest tenth, hundredth, whatever. This would be an approximate value. So we're doing more complex examples than this today. So here we have solving, where we want to leave our answers as exact values. So what's going to happen is you're still going to have logs in your final answer. So this first one, log of 3 to the power x equals log of 5. What you're going to do is apply the log laws that we've learned in order to bring the x out in front of this. We can't solve this right now when x is in the exponent and there's logs on both sides. So we want to get that x out of the exponent. Here you can see I've brought the x in front and it's multiplying by log 3. This log 3 is just a number. If this was the number 2, you'd see what needs to be done quite simply. If you have x times 2, what would you do to get rid of timesing 2? You would divide both sides by 2. We're doing the same thing with a more complicated looking number. The number is log 3, but it's the same algebra you've been doing since junior high. So here you can see division of both sides by log 3. When you take a number and divide by itself, those cancel and you're left with x on the left and log 5 over log 3 on the right. Now here's a clip from your formula sheet that shows how you can say two things dividing as one log. This is our change of base formula. So all I've done here, this is a perfectly fine answer, but you might see it written like this instead. This is where you take C and B and you place them in one log in those corresponding locations. Next example, first check for like bases. Is there any way of making 5 and 3 the same base? No, there's not. So we're going to start with this step over here of taking the log of both sides. In algebra, whenever we do something, we do it to both sides. Doing the log of both sides is a valid algebraic step. Here you can see I've just put log in front of each of these exponents. Next step is going to be applying a log law. The exponents have x, and we want x down in the regular line of text. We don't want it in the exponent. So here comes the exponents out in front. Now, this one is more complicated because it's a binomial. What you need to do, thinking again, this is just a number. If this number had been written in front, let's say there was a 10 in front, we would do distributive property and multiply the 10 through. It's no different with log 3, it just looks more complex. Log 3, you're going to use the distributive property to multiply into the brackets. 2x times log 3 is written right here, and negative 1 times log 3 is written right here. Okay, so you wouldn't see this part yet. So if I was writing this on the board in class, you would only see what's above my cursor right now. Next thing you want to do in algebra is you want to get all of your like terms on the same side. So what we've done for years is put all of the x's onto one side of the equation. That's what you can see me doing here. This is some kind of number with x. Pretend like it was just 2x. How would you move 2x to the other side? You would minus 2x because it's the opposite of plus. What you do to one side, you would do to the other side. That's what you can see me doing here. I'm moving this x over here so that it can be with the other x. This one will cancel and we get just negative log 3. And on this side, you can see any term that has an x is now collected together. Now these numbers are different. 3 log 5, 2 log 3, those are different numbers. We can't just combine them together. So what we have to do is factor the x out of this expression. So what's going to happen is it's a GCF of x being written in front, and then when you divide both of these by x, the x's would cancel. The numbers and the logs are the only thing left if you take these x's out. So imagine these x's disappearing. You would have 3 log 5 minus 2 log 3 left. Now, what do we do if we have some big complex number here and we want to get rid of it and move it to the other side? Well, we do the opposite of whatever this big bracket is doing with x. What it's doing with x secretly is multiplying. You can write a dot there if it helps you. So the opposite of multiplying is dividing. I'm going to divide by this entire complicated looking thing. Don't let that confuse you. Just write the same thing below and write the same thing below here. Now this is going to be the most complicated looking answer you've ever seen in math, but that's okay. It's going to have a lot of logs, division, negatives, all sorts of stuff. But this is the exact value of x. If I wanted you to round, you would put this in your calculator and determine the decimal value. Let's try again. Checking first for like bases. 3 and 8 cannot be written with like bases, so we're going to start by logging both sides of the equation. After I've done that, the x's are in the exponent. They need to come down in front of the log. So I'm going to use my log law to bring the exponents down in front. Now, these ideally I would highlight because these need to be in brackets. Our next step is to do distributive property, and if you don't see brackets, if you imagine this without brackets, it would look like 2x minus 3 log 8. It would look like it was already done. So we need to write the brackets so that the log 8 applies to both terms in the binomial. Same thing on this side. X and 2 both need to multiply by log 3. What does that look like? X log 3 plus 2 log 3. This side 2x log 8 minus 3 log 8. You're simply multiplying these by log 8. So put log 8 behind those two terms. Now this one has more going on than the last one. You have to look at each term and determine the ones with x's, bring those over to the left, and the ones without x's you're going to bring to the right. This is a step in algebra where we'll be adding or subtracting. So I wanted to bring this 2x over. It was positive, so I subtracted it. I wanted to bring this 2 log 3 over. I subtracted it because it was plus. Now there's no way to combine these without getting decimals, so you simply write negative 3 log 8 minus 2 log 3. Same thing on this side, x log 3 minus 2x log 8. Now you're at the point where you're ready to GCF the x out of this side and write the logs that remain. Nothing needs to happen to this side. Once you've GCF'd the x out, you're going to divide both sides by this entire bracket. Okay, that's what you can see me doing here. This side will cancel to give you just x. This side is your answer. Now you can see in red that I've put brackets here because if you want to put this in your calculator and get the right answer, you're going to need to bracket the top and bracket the bottom. Okay? The other thing that I'm showing here is that this can be written as an equivalent number by multiplying top and bottom by -1. Okay, you might not see this in the multiple choice answers, but you might see something where all the signs are completely opposite. That's the same number. If I multiply top and bottom by -1, -1 divided by itself is the number 1. Multiplying by 1 doesn't change the value of what this is. So if you change every single sign, you get the exact same term. So when you're looking at your answers on the worksheet and mine, if you had every single sign the opposite, so for example, +3, +2, negative log 3, and +2, you would have the same number as me. All right, this one has some multiplication happening on the left-hand side. We still want to see if we can do anything with like bases. 6, 3, and 2 unfortunately can't have like bases. So we go ahead and we log both sides. Now this is going to bring into play another log law. This 6 and 3 to the x minus 2 are multiplying together. So when you have multiplication of two things within a log, that's going to break down into two logs that are adding together. That's what you can see me doing in this step here. I'm just bringing down this log 2 to the x and bringing the x in front on the right-hand side, but really a lot is happening on the left-hand side. So the multiplication became plus, the exponent came out in front, the binomial, we did distributive property to multiply log 3 through, and now we have 3 terms on this side and 1 on this side. You do have some options. I tend to bring my x's to the left and all of my things without x are going to the right, but you can do that the other way. You could bring this x term to the left. It doesn't matter. That's what I'm doing in this example, but this is the step where it might look different if you bring things to a different side. Here you can see all of my logs that don't have x's in them, and here you can see all of my logs that have x's. I'm ready to GCF this x out in front and write the logs that were with them and divide both sides by that entire bracket. So this side, nothing changed. I divided it by everything in this bracket. All right, this example again has a number in front, but this one is different than the last example. On the last example, this term on the right had an exponent of x. Remember, you can't have an exponent of x and then divide by a number. That's not allowed. Since this 568 is just a whole number, and it divides by 8 nicely. See, 8 didn't have an exponent of x either. That's going to make this a much simpler question. You can go ahead with the same process that we got on the last example, and you can log both sides off the bat, but if you can divide like this, all of a sudden this is more of a 7-rule question than it is logging both sides. So I've done this 2 ways. This side, I've logged both sides. This side, I've taken this first step and I've applied the 7 rule to it. And you can see this is a much simpler solution. Okay, this is not wrong, however. This is the same thing, logging both sides, bringing the 2x out in front, and dividing by the numbers to get x by itself. The 2 and the log 3, divide by them, and you get this. Now take a look at this. If we use our change of base formula, log 71 over log 3 is log base 3 of 71. These are the same number, but they look quite different. So this is something you'll have to notice. A lot of times if you're dividing two logs, there's nothing adding or subtracting here. They can be written as one log, and the 2 stays in the denominator. All right, that's it for this lesson. So corresponding to 2.8 is a worksheet that's posted on the website. Including this lesson, a total of 1 hour of work is all you need to be doing for this week, and next week you can expect more lessons from me. Reach out if you have any questions. I'm happy to help.